It's our pleasure to have Arpita Patra here today, and she'll be telling us about the communication complexity landscape of Information-theoretic MPC. So thank you.
Thank you for the kind introduction, Elliot. And thank you to all the organizers for having me here and organizing this very useful workshop. And thanks to all of you here for being here. So let's begin. So I'm going to talk today on the communication complexity landscape of information-theoretic multi-party computation. So at a very high level, MPC permits a collection of distrusting data owners to perform a collaborative computation on their private inputs in a way that nothing beyond their function output is revealed. And the distrust is modeled by a centralized adversary who can corrupt T out of the in parties. And so far, MPC had been studied in various settings. And in this talk, my focus will be on the information-theoretic security. So at a high level, I want the view of the adversary should be either perfectly or statistically simulatable from the input and output of the corrupt parties. So these are major complexity measures of MPC as we have seen in Yuval's talk yesterday: communication, round, and local computation. So having spent quite a bit of time on the round complexity of MPC, I thought of giving it a break. And in this talk, I'm going to talk about the communication complexity. So as you know, communication complexity is one of the expensive resources in cryptography and distributed computation. And therefore, a huge amount of effort has gone in characterizing the amount of communication required for various cryptographic and distributed computing tasks. And in this talk, I'll be focusing on the communication complexity of the general multi-party computation. So just to be on the same page, these are the settings, the fundamental settings of MPC that I will be focusing on in this talk. So as far as the network is concerned with, over which the parties are connected with, I'm going to consider the popular choice of synchronous network as well as the asynchronous network, which is more realistic. And of course, since I've been mentioning about information-theoretic security, our adversary is going to have unbounded compute power. We're going to consider both passive as well as active. While the passive will be used mostly for the lower bounding purpose, the upper bounds are going to be secure against active adversaries. And the security that we will be bothering about is information-theoretic, and we will consider both abort as well as guaranteed output delivery. Abort, again, is mostly for the sake of giving lower bounds, and the upper bounds are going to be guaranteed output delivery or robust. So these are some of the most fundamental settings of MPC. And even in this space, you would see there were a lot of open questions, and there are actually still a lot of open questions to be solved. OK, so I guess in the previous slide, you know all the terms, but I thought I'll just make this clear, the distinction between synchronous and asynchronous networks. So the synchronous is what everybody would expect, right? So every message in the network will be delivered within a known fixed time, right? So there is a known delta that everybody knows about it, and the messages will be delivered, every message in the network will be delivered within the delta time. So typically protocols in synchronous network, they proceed in terms of rounds, right? So first delta time is for the first round, then the second delta is for the second round, and so on. And within every round, the parties are going to send out messages to every other party, going to receive messages from others, and they're going to do some local computation. Okay? And this is what is going to be repeated in every round. And this delta, we'll see how it is set in the next slide. So the other point about synchronous network is that the messages are not going to be reordered. On the other hand, the asynchronous is probably the other extreme, right? So here every message sent will be delivered eventually. We do have that guarantee, but we don't know when, right? And the messages can be reordered, and the worst of all is that the message scheduling is controlled by the adversary. Okay, even if we are talking about channels between two honest parties, the adversary doesn't get to see what's going on between the two honest parties, but it gets to schedule the messages that are going between the honest parties. So in summary, in the synchronous setting, all messages sent between the honest parties will arrive within some bounded delay delta, and typically the way we set this delta is as the max of all the deltas of all the channels in the network, right? And if delta is too large, and by the way I have explained how the delta is chosen, you can see that even though there are very few channels which are extremely slow, that's going to drag our delta to be a very large value, right? And if delta is large, then of course the protocol is going to be very inefficient and slow, especially when the protocols has very high round complexity. And if we don't choose the delta the way I said, so then in order to make the delta to be small, then we may lose security, or even it can lead to non-termination. On the other hand, in asynchronous setting, every message sent between the honest parties will arrive within some finite yet unknown delay. And as I said, the adversary can delay the messages between honest parties, but those messages will be eventually sent or delivered. Now there is this very fundamental phenomena that happens in asynchronous network, which poses a huge challenge in terms of designing protocols, and also you will see that it puts some penalty in terms of the resiliency that we require for a asynchronous network. So the phenomena is as follows. So in asynchronous network, we cannot distinguish a slow sender from a corrupt sender. So consider the following scenario. Let's say you have a sender and the receiver. At some step, the receiver is expecting some message from the sender. Okay, and let's assume the receiver is not receiving. Now, what can it conclude? So it can happen that the network is synchronous, but the sender was corrupt and it didn't send the message. Otherwise, it can as well happen that the network is asynchronous and the sender was honest. It had sent the message, but it's just taking time, right? The adversary is scheduling the message, so it's just taking time. So from the receiver's point of view, it's totally indistinguishable, these two scenarios. And therefore, most of the distributed protocols in the asynchronous network has to follow the following rule, that at any step, a party, whenever it receives n-t messages, then it must have to proceed. It cannot wait for more messages than n-t messages, because if it does so, then it is possible that the protocol will not terminate, the party will not terminate, because it could have been that those are bad parties and they have not sent the messages to you. And then if you do this, then there is a bigger problem, because it can so happen that the messages an honest party would have missed could belong to the honest parties actually. Right? So so in the worst case, an honest party would miss the messages of other honest parties, and it would actually include the messages of corrupt parties. So this is a problem that we had to deal, and this poses a lot of problems in terms of, challenges in terms of designing protocols in asynchronous network. And the good point is that about asynchronous network is that it's a very realistic network. So it is said that internet models asynchronous network actually, right? So and if you have smaller delays, right, most of your channels in the network have smaller delays, then most likely the protocol is going to move in a very faster speed. And this comes from the practitioners, applied cryptographers, I guess. So they say that asynchronous MPC is much faster than the synchronous counterparts, in particular when the protocol has many number of rounds of communication.
In the blockchain community, I don't know how relevant, but there was a lot of deal made recently about this partial synchrony. Apparently, it brings some advantages.
Yeah.
So is it relevant to us, or we are like too theoretical together?
So I don't know which one I don't know which one you are talking about, but the notion of partial synchrony has been looked at, and there are various notions of partial synchrony. So I'm not sure which one you are referring to. So in some cases, for instance, they assume that let's say the first few rounds it could be just one round is synchronous, and after that the network turns totally asynchronous. And that seems to bridge, in some cases, the the stricter resiliency requirement that we have in asynchronous network.
I mean, like specifically for consensus, I know like Victor Schupp has some consensus, I forgot Kunze or something, but my understanding is a synchronous model is too impractical for them. Synchronous is completely useless, so this partial synchrony seems to be, so somehow in practice it seems to be all the recent things at the SBC conference and this partial synchrony. My understanding was like the opposite, that it starts as synchronous, but then after some period becomes synchronous. Somehow, but I'm not sure.
Oh, it started asynchronous and then it becomes...
That's my understanding.
Okay. I don't know about that one, but I mean, it is possible. People have experimented with partial synchrony a lot. There are many different notions. Okay, so now let us move on to see what are the resiliency requirement for perfect security, both in the synchronous as well as in the asynchronous network. So if we look at the synchronous network, then the seminal work of BGW from 1988, they show this fundamental theorem that any function f can be computed with perfect security in the presence of t less than n by 3 malicious corruptions. When you go to the asynchronous network, the same result takes t less than n by 4, and this is the penalty that I was talking about. So you need more honest parties in the system, and I mean that's the necessity in asynchronous network. Now it appears that these two lower bounds so far they hold good for when the protocols are expected to give guaranteed output delivery. So recently we just asked if the same bounds hold good for even when you relax to a bot security, or whether you can get a better bound. So we found out that actually even when you require just a bot, not guaranteed output delivery, still these bounds are they hold good. Okay. Right, now we will look at all the great work that has been done in the regime of synchronous perfect MPC for improving the communication complexity. And typically here I'm going to talk about the complexity per nonlinear or multiplication gets. So of course it started with the work of BGW, which had a relatively higher complexity per multiplication, n power 7 or something like that. But soon, I don't think it's very soon, but it converts to a linear complexity protocol in back in 28 by this work. They had a small caveat that in order to get the linear complexity, linear overhead per multiplication get, they had to increase the round complexity to d plus n. So the work of BGW had a round complexity which is just linear in the depth of the circuit. And these two works, they have built protocols while with the round complexity being dependent on both d as well as the number of parties. Okay. And that in some scenarios it may not be nice when, especially if you have a large number of parties. So there are still a bunch of people who believe that even without doing that compromise, increasing the round complexity, you could still do the same thing. That is, you could achieve linear complexity. And that line of work culminated in that work of ours, where we show a linear overhead MPC protocol with still order of d rounds.
Slice the circuit into log like Bar-Ilan Beaver and get shave a log factor with polynomial increase to the communication.
Polynomial increase in the communication. So okay, so you could do that, I guess. So then it will be n times some polylog of circuit size overhead.
You can shave a factor of c in the round complexity by paying a factor of 2 to the c with other measures.
Yeah, you could do that as well, I guess. Yeah. Okay, so Right, so this is the state of the art. But now we ask this question while people stop that, is it optimal? Okay, we don't know, we'll see. Okay? But let's move on to the other network style, which is asynchronous. Again, we stick to the perfect case. So over here, I guess the convergence to the order of n overhead MPC took quite some time. So it started at 1993, and finally, around 2010, we had a quadratic communication complexity solution. Finally, in 2024, we gave the fast linear solution. But it's worth the wait, I guess, because our protocol actually again gives a constant order of d expected running time, whereas the earlier protocol takes an extra log n factor. Okay. Right. Okay. So again, we are stuck at order of n overhead, and we ask the question if this is optimal. We don't know. Let's see. So the answer is actually in this slide. So over here, we have given two lower bounds, one for synchronous and the other for asynchronous network. So the first one says that in the synchronous network with n number of parties where n is 3t plus s, right, the communication complexity overhead must be n by s. And the same bound holds good for asynchronous, but with different number of parties, which is 4t plus s. And this result holds good even for abort security. Even though you don't want guaranteed output delivery, you want just abort, still this result holds good. So now if you put s equals to 1, that gives you the optimal resiliency for both the settings. And you can see that linear is the overhead that you need per multiplication. So this is the price, that you pay for optimal resilience.
Does this lower bound assume any structure of the protocol, like the protocol has to work gate by gate or something like that?
Yeah, so these are for some special kind of functions, which are called linear size, linear in the input size. So the theorems basically say that for any input size s, there exists a function with s gets, and it's going to cost you n times s number of.
So it could be the case that there is a protocol that works with n cubed, right? For every circuit.
Mm-hmm.
Yeah. Okay, so this is what, so if you put the value of s that I have already said, so now if you have to achieve something which is sublinear, then as you can see, we have to set the value of s to be theta of t, right? So you need that extra number of parties in the system in order to get to linearity. And as you know, so we can use techniques like packed sector sharing. I'll come to those things. So those can be useful if you want to get constant time protocols. So I just summarized those two extreme cases in terms of the upper bounds in these two slides. So first, I have set s equals to 1, and in that case, the complexity requirement is order of n overhead. And these are the papers which have given order of n overhead protocols. And the security is not just about it's actually guaranteed output delivery. In fact, people have gone extra 1 mile to provide protocols where they have pushed the order of n requirement to the offline phase, and the online phase is just constant overhead. So those protocols are also there, right? So this is the best you can do. You still need order of n, so what you can do is that you can push that order of n to the offline, and online becomes constant. Right. And again, if you set the value of s to be theta of t, then you can achieve constant overhead with guaranteed output delivery. And this is the work where we provide this. And currently, I claim this only for s equals to theta t, but my conjecture is that the constructs are tight for even super constant values of s. We are checking that, but most likely that's going to be true.
What is the conjecture exactly?
Oh, the conjecture is that, so we had the lower bound for general S, 3t plus S and 4t plus S, right? And the complexity is n divided by S times the circuit size. So we think the protocols that we have, and which I'm claiming right now for S to equals to theta t, holds good for the for super constant values of S.
But we don't know that it has to depend on the circuit size.
We don't know.
It's only for protocols that go gate by gate, not for general protocols.
Yeah. It's for gate by gate, yeah. So it's for the kind of circuits I have mentioned, but so for linear size circuits, these lower bounds are true. But so far, all the protocols that we know, they give the similar purpose to, similar approach to all. Given a circuit, they do the same thing, right? They don't do different things currently.
So this is the cost of the compiler. Like if someone has a better representation of the computation, then it's fine. Like this is the cost.
Yes, this is yes.
Okay. And just a quick question: what is the asymptotics in? Like if you are considering, are you considering asymptotics in N or?
Which one? This.
This is all this.
This one?
Yeah. Is asymptotics in N or in some other?
In N, yeah.
N.
The number of parties.
So you need a family of circuits that, for lower bounds, what do you show? Do you show a family of circuits that cannot be computed?
So basically, we talked about the linear size circuits, right? And so there we reduced to string OT actually. So where the communication complexity will depend on the length of the strings of the sender.
Just to place both these things, lower bound is n over s. You have upper bound, you have n over s for s theta t, but you think the same protocol would work for all s's up to super constant.
Yes. All right, so as you can see, I mean, the way I have discussed the perfect case is almost sorted. So one thing that we have noticed is that the upper bound that I have just mentioned in the previous slide, when S equals to exactly 1 and it works for the tight resiliency, then it actually doesn't give the optimal complexity. So it suddenly becomes n squared. It's no longer order of n. So maybe one can try to design one protocol that is optimal for the entire range of S. So that could be one interesting question. Okay, so I guess that was the thing that I wanted to say for the statistical, for the perfect case. Now I will move on to the statistical security case. So we will start again the same story. So we will start looking at the optimal resiliency required for the statistical case. So for the synchronous network, it goes to the seminal work of Rabin and Benor from 1989. Says that any function f can be computed with statistical security in the presence of t less than n by 2 malicious corruptions given a broadcast channel. And again, you see a similar pattern. If you go to asynchronous network, then the requirement is that t should be less than n over 3. Again, we can prove a similar result here, that even though you relax your requirement to abort instead of guaranteed output delivery, still these bounds are fine. I'll wait. I could not get a picture. So I searched for it, but I couldn't get a picture. Maybe you can help me to fill in. Yeah. Okay, now let us look at the similar landscape for synchronous statistical MPC protocols. So I did not exactly check the complexities, but most likely they're equal or higher compared to n power 7 per multiplication. And in 2012, the first linear protocol was obtained. And later, this was improved in the sense that the linearity is obtained also for the term which is dependent on the depth. Earlier, that was not the case. So the last work achieves that as well. These last three works, they require order of d plus n square number of rounds because due to dispute control framework, they use dispute control. So naturally, it inflates to n square. So, but then we don't know of any linear protocol which has round complexity, just dependent on d.
So you don't assume
We assume. We assume a broadcast channel.
Also, these are like technically incomparable models to the previous one, right?
You could say so, yes. Yeah.
You cannot assume do it without broadcast channel.
Oh, you cannot implement it or something?
No?
You cannot from scratch, so you need some setup to do that. Yeah. All right. Again, the same question: is it optimal? We will see, and we move to the next one, and this is the last one. This probably is people are scared about this, this cranky combination of asynchronous and statistical. So it's very few people have looked at since its inception in 1994. So we did some works over here back 10 years back, which finally culminated in this work in Journal of Cryptology last year, where we have quoted the communication complexity to be n power 4 per multiplication. And recently, last year, these two papers together, they lead to a protocol which is which gives you the linear overhead. Okay. So again, we ask if linearity is required or necessary or not. Right. So the answers are there in the next slide. And over here, there are two lower bounds. The first one comes from this work by Ivan and Casper and Jesper. So they have shown that in synchronous setting with resiliency 2t plus s, the complexity overhead is going to be n divided by s. And this is true even for passive adversary. Okay. Whereas for the asynchronous network with 3t plus s, we show that the bound is true, but we could prove this only for abort security, malicious abort security. And again, you see a similar pattern. So when you set the value of s to be 1, that gives you the optimal resiliency, but then you have the overhead of order of n that is required. So that's the price you pay for security. So that is those are here. Those results are here. And the other extreme, when you set the value of s to be theta of t, then the lower bound says that you can get constant protocols, and we do give one with we actually consider both settings. So we have two protocols with guaranteed output delivery. And again, I make the same conjecture here that these protocols are tight for all super constant s. Okay. So it says ePrint. You may not find it yet in ePrint. We are uploading it again in 2 days. I thought they will be uploaded before I give the talk, but we are doing the last minute changes. Right. Okay. So as again, I guess the statistical case is almost all sorted. And I pose the same question over here, that if someone can design one protocol that would work for the entire range of S. Okay, so in the next few slides, I'm going to give you some technical highlights. I mean, the techniques that we typically use for designing this kind of protocols. So the first one is how to verifiably share a secret. So all these protocols are typically designed based on linear secret sharing schemes like SAMIs. So in SAMI, you hide one secret.
Sorry to interrupt.
Yeah.
Just before, all the results you talked before were static, not the upper bounds. Like
they will all work for adaptive adversary.
Adaptive adversary.
Yeah. Okay. So yeah. So the SAMIs protocol hides one secret, and at the cost of order of n, n shares, right? So the overhead is order of n. So this acts as the basis for the linear protocols that I had claimed in the previous slide. And when we want a constant overhead, then we move to the domain of packed secret sharing, where you could, in theory, pack many values, but we need to pack theta t values, and the cost is same as SAMIs, order of n. So in amortized sense, per secret, the cost becomes order of 1, right, constant. So for designing optimal MPC protocols, depending on the settings, we need verifiable secret sharing to achieve this sort of secret sharings with constant overhead or linear overhead, depending on the application case. The next one, the next primitive that we need is of verifiable relations. So here a designated party. So in the previous slide, a designated party shared a secret. Here it will share a relation. For a relation could be, I mean, the most popular relation is actually the generating the multiplication triples, right? So this would build on top of the previous primitive, where you need the verifiable secret sharing, and on top you would need a proof, a zero knowledge proof that the shared thing satisfies some relation. Right. The third building block is extraction of relation, wherein the parties, everybody is going to share the relations, either in the non-packed or in the packed domain, depending on the scenario. And then finally, we want to extract out some relations which are not known to the adversary. So over here, some parties are corrupt. They know the values that they have shared. And out of all this, we want to extract out some triples in a very efficient way. I mean, triples is one kind of relations where they are not known to the adversary. So that's the goal over there. And the last one, this will be used mostly in the online phase. If you remember, so we are building Weaver type triples, either in packed or non-packed domain. And we're going to use those triples, consume those triples in the online phase in order to evaluate the multiplication gets. And typically, if you remember, we need to reconstruct these two values, x minus a and y minus b. That could be looked at more generically as a degree reduction. So they will be shared, if you consider the Samir domain, they'll be shared with t degree. And then you want to reduce the degree because you want to reconstruct so the degree becomes 0, right? In the packed domain, you will see that we need actually 2 degree reduction, specifically of those kinds where p is actually the packing parameter, how many values you are packing. That's what p is. So irrespective of the previous things, if we actually could do the degree reduction with the constant overhead, then it leads to constant overhead online protocols. Even though your offline is linear, if you could design the degree reduction with constant overhead, that gives you order of 1 online phase. Okay, so this is the blueprint I really discussed in the previous few slides. So you have this offline, and then you have the online phase. In the offline phase, you try to generate Weaver triples, and that reduces to the multiplication triple getting generated by a single dealer, which further reduces to verifiable secret sharing and a proof that they satisfy the product relation. So I don't know how much time I'm left with. So in the rest of the time, I just want to talk about 2 techniques. In one case, we have actually designed a variant of verifiable secret sharing, which is called weak binding verifiable secret sharing, which we use to design the zero knowledge proof for the product relation. So I wanted to discuss the protocol itself, and that led to that work. And the other one that I want to discuss is how to do this degree reduction, which gives us order of 1 overhead per multiplication. So the first thing, the weak binding VSS, that leads to this theorem that for any circuit C with multiplication gets and C multiplication gets and depth D, there exists a perfectly secure, optimally resilient asynchronous MPC protocol with this much communication complexity and order of D expected round. And the other one will lead to this actually many theorems, nice theorems. The first 2 says that there exists an asynchronous perfect MPC with n greater than 40 parties and a constant communication overhead in the online. So as I said, that's going to impact the online phase, and that's going to make the online phase constant overhead. That also has some implication with some additional techniques in this regime, synchronous statistical MPC with 2t plus theta t parties. So let's see. So I'll start with the first one first. So we'll see the definition of asynchronous VSS or AVSS, and then I'll say what the weak version of it means, and then we'll try to build a protocol for that. So asynchronous VSS, just like in the synchronous world, has 2 phases, sharing and reconstruction. In the sharing, the dealer has a secret which it wants to distribute amongst n parties, and in the reconstruction phase, the shares should be put together to reconstruct the secret back. So we want these properties at a very high level, validity, which means that if the dealer is honest, then the protocol must terminate, and in the end of the reconstruction phase, the honest parties must output the input of the dealer. Security, which means that the view of the adversary in the sharing phase must be independent of the secret. And lastly, the binding, which says that the view of the honest parties at the end of the sharing phase must uniquely define a secret, and the same secret must be reconstructed in the end of the reconstruction phase. Now, what do I mean by this weak binding? This is what we need for weak binding. So here still, the view of the honest parties at the end of the sharing phase should define a unique secret, but the reconstruction of the unique secret is not guaranteed. Okay, so we give away that property. And it's very nice, beautiful how the sharing phase of a weak binding AVSS guarantees that zero knowledge, so that's a different thing. But here I'm going to focus on how we achieve this weak binding secret sharing with certain complexity. In other words, actually we achieve order of 1 overhead, that is per secret the cost is going to be just constant. So we use two techniques, packing and batching. So typically if you look at the traditional VSSs, they use bivariate polynomials and they just put one secret in the constant term. So what we are going to do is that we're going to pack in both dimensions, along x and along y. So I've just taken some examples, t by 2, but we can change that. But in general, you can pack theta t secrets in each dimension. So that allows you to pack theta t square values under the bivariate structure, and as you can see, bivariate structure already needs a communication of order of n square. So that intuitively gives you a constant overhead. So yeah, so over here we are packing n square secrets, and then we have also observed that broadcast in VSS, it takes a huge amount of communication. To be very specific, you need this pairwise broadcast of for every party broadcast something for every party, every other party. So that means n square number of broadcast, and if you take, I guess the best known broadcast without the multi-valued or extension version takes n square. So that takes the broadcast complexity to be n power 4. Okay, so what we do is that we run n square instances of these VSSs and we combine the broadcast for all of them. So there is just one set of broadcast for all the n square VSSs, and that way the cost of broadcast remains the same for the n square instances. So that way the cost will be n square, n power 4, and the number of secrets that we will be actually hiding is also n power 4. Because there are n power 2 bivariates, and each we are hiding n squared. So that gives you n power 4 secrets. Okay, this is the way we achieve the constant overhead. So let's see how we do it. It's a very cute trick. So as usual, all those who are familiar with the literature of verifiable secret sharing, so this is what we do. There's a designated dealer, and it has this theta of t square number of secrets. It plants them in the right position in the bivariate, and then it gives the ith row polynomial and the ith column polynomial to the ith party. Okay, that's how the distribution of the polynomial happens. And then the parties will sort of check the common points that they have, whether they're okay or not. And based on that, a consistency graph is constructed. So you join a line or add an edge between two parties. So the nodes over there in the graph, consistency graph, are representative of the parties. You add an edge if they are consistent with each other. Now, one thing you can do is that you can try to see how many are consistent with each other, because that will sort of tell us whether there is a unique bivariate polynomial committed to the honest parties. So assuming that if you can agree on a clique of size n minus t, right, that solves the problem. Assuming that, okay, the clique finding works, polynomial time, no problem. So then it works, right? Because you have 3t plus 1 parties who are consistent amongst each other. they have confirmed that their common points are same. Within these 3t plus 1 parties, you have t parties who are bad, but the remaining 2t plus 1 parties are good. And their univariate polynomials, their row and column polynomials are consistent with each other. So that defines uniquely a polynomial, bivariate polynomial of degree t plus t by 2 in each x and y. Now the question is, of course, we know the clique finding doesn't work. It is inefficient. So how are we going to replace that with, right? What are we going to do? So there is a result. This comes from Canetti et al. So they show that you could instead find a structure in the graph which is called star, and that would work for most of the cases. And here's the specification for star. So it looks for two sets of nodes, C and D, where C will be of size 2t plus 1. Actually, this is n minus 2t. So in our case, n will be 4t plus 1. So that's why it is 2t plus 1. And D is a superset of C, and it is of size n minus t. And in this case, it is 3t plus 1. And there is edge between every C in this pass set to every node in the second set. So they are all consistent with each other. So if you look at C, that's actually a clique, a smaller clique. And that's easy to find for this graph. Right? So that work, they give a polynomial time protocol that can find such a clique if the graph contains a 3t plus 1 clique. And it can find a star if the graph contains a 3t plus 1 clique. Okay, so there's a polynomial time solution for that. Now let's see. In our case, can we replace the clique finding with the star finding? Let's see. So instead of a clique, we now use a polynomial time algorithm and find a clique, find a star instead. What do you think? Does it work? No, right? Because now C contains just 2t plus 1 parties, and within this 2t plus 1 parties, you have only t plus 1 parties, to be honest, and that's what is guaranteed. And they don't define a unique polynomial of degree t plus t by 2 in both x and y. So the commitment is not guaranteed for this structure because we have increased the degree. And we had to increase the degree because we have packed a lot of secrets. Right? So it appears that we need a big star. And by big star, we mean that the C, the first subset, will have a bigger size, which is not 2t plus 1 anymore, but it has extra t by 2 parties to accommodate for the degree increase. And now everything will work fine because C has 2t plus t by 2 plus 1 parties, and within this only t parties could be corrupt. Still you have t plus t by 2 plus 1 honest parties, and their rows and column polynomials, because they said they are consistent, and they would define a bivariate of this higher degree. So that would be fine. But then we don't know a polynomial time algorithm for finding this extended star or the big star. We don't know at least how it works. So this is where an idea has been used where we move from the typical use of bivariate in the VSSs to trivariate. And what trivariate gives you will see in the next slide. So instead of bivariate, now we have a trivariate polynomial. So we are packing order of n cubed or t cubed number of secrets, and to every party we give the row, column, and whatever the other dimension, the cube, right? So and the consistency graph is made in the same way. Of course, we have now more equalities to check. Earlier for bivariate, every pair of parties had 2 points in common. Now they'll have to check for 6 equalities, right? So that's what they would be checking, and they will make the graph. And now when they make this nice observation that if you talk about 2 parties, right, and if, let's say, they don't have any edge between them, but their degree is high enough, each of them have degree, let's say, at least 3t plus t by 2 plus 1. So what can you say about the number of common neighbors they have? So total number of parties is 4t plus 1. And since each of them have degree 3t plus t by 2 plus 1, it means that they have 3t plus 1 common neighbors. So this actually implies that they both are consistent, even though they have not cross-checked against each other. So this is called transitivity, and this is first noticed by Benny and Elran. and we're going to use this. So if you have not understood it, so I have a detailed picture in this slide, which hopefully would make the situation better. So let's say the Alice has the first bivariate polynomial, which is s of x, y, 1, the blue one, and Bob has this red bivariate polynomial, and together they want to check if this univariate polynomial lies in their intersection. That's their goal. But it's been an asynchronous network, so they let's say they could not talk to each other. Their communication is blocked, so they could not talk to each other and check the consistency. But this third party comes in the picture, right? And this party has this bivariate polynomial, which is represented by the green plane, right? And it is okay with with Alice through this univariate polynomial, and therefore it checks for this point. And it is also okay with Bob with respect to this line, right? And it confirmed the consistency of this point. So this party is individually consistent with both Alice and Bob. And if you have enough number of parties like this, then they will make sure that Alice and Bob, even though they have not directly checked with each other, they are actually consistent with each other. So this is what we use. So basically in our consistency graph now, we will try to find sufficiently many number of nodes with high degree. High degree means 3t plus t by 2 plus 1 in our case. So if we find actually 3t plus 1 such parties, nodes in the graph, then we'll call that graph as dense graph. So it has sufficiently many nodes with sufficiently big degree. And what does it imply actually? So if you have this much degree, just by the previous result, you can say that every pair of parties in this set, they are actually consistent with each other. So that actually implies a clique of size 3d plus 1. But what if you don't find that many number of high degree nodes in the graph? Then we have an alternative thing. Then we say that there is a way you can find a big star. If you don't find that, then we find this. So either one of these two works, and both of them actually guarantees a clique of size t plus t by 2 plus 1 honest parties who will be pairwise consistent, then they will guarantee the uniqueness of the secret committed. Right, so a little bit in more detail. So basically, if you don't have 3t plus 1 number of parties having that many number of degrees, then you do have at least one honest party who has less degree than this, which is this, right? And the honest parties will have, so that means that particular party will have t plus 2 plus 1 corrupt non-neighbors. So if we remove the neighbors, the non-neighbors, and then run the existing star finding algorithm, then it seems that it will actually give us a big star. Not just star, it will give us a big star. So that's the end of it. I'm not sure how much time I'm left with. 6 minutes, okay, that's fine. Then I can, so that's the first technique that I wanted to discuss. And now I will just talk about the other one, which leads to this constant overhead online phase. So for this, first we need to look at, we have to be in the packed domain. So everything happens here in the packed domain. So if you recall, this is what happens. So we use polynomials of a higher degree. So if you want to pack p secrets, then you'll have to raise the degree of the polynomial to this, and this gives you constant overhead per secret. So basically these are the secrets that you are packing, and we'll be using this notation. So assuming that everything is given in the packed way, so you have the triples which are already given in the packed setting, you have the inputs which also are given in the packed way, then it appears that we need to reconstruct these two sharings. But the degrees are more now, and we have to do it with constant overhead. So for now, assume that we want to do that, and we have, let's say, semi-honest corruption, and we have synchronous setting. So the simplest setting that you can think of. So what would you do to get order of 1 cost for the reconstruction, what would you do? You will use the peaking best approach, right? So you just choose one party and everything is reconstructed. All the shares are given to that party. That party will recover S, and then you can't send all the values in S to every other party, just like you did in Beaver. You can't do that. Why? Because you want constant overhead, and S has theta of t secrets. So if you send to all the parties, then it will cost you order of n squared, right? So what instead can be done is as follows. So you will find an RS encoding of the secrets, and then you will just give one value of those encoding to every party, right? So now the degree becomes p minus 1 because there are p values. So you make a p minus 1 polynomial out of them using RS coding, and then you give one share to each party. And this works. So this is why I said that instead of reconstruction, now we'll call it as degree reduction, right? So from this degree to that degree is what we have gone to. Now this is fine in semi-honest and synchronous. But what happens if you are in the malicious setting? This party may not be honest anymore, semi-honest anymore, and it can actually change the secret. So Ethan has a work, and he has done a lot of trick to make sure that the party can be checked for its correct behavior, that it has shared the same secrets. So something like that could be used for malicious adversary. But what about if you are in the asynchronous network? What do you do then? You can't use the same tricks, right? Because again, it's a single party, and you never know whether it's corrupt or its message are going to be delayed. We can't rely on that. So we propose a technique which actually work with both the cases, whether it is malicious or asynchronous. In most of the settings, the resiliency settings is what I'm talking about. So let me talk about that. And just before that, before I go to the technique, I just wanted to say that while we run the Beaver in the online phase with the packed secret sharing, then there are 2 degree reduction that needs to be done. One is for that x minus a and y minus b. So those has to be reduced from t plus p minus 1 to p minus 1. And there's another instance which is this, right? So this is the equation. So what happens over here is that now this reconstructed values are no longer of degree 0 that it used to be in Beaver's case. Now they have degree p minus 1. So when you multiply this 2, the degree inflates to t plus 2p plus minus 1, right? So in order to get the invariant, because we need all the shares to have this degree, we have to make another degree reduction from t plus 2p minus 1 to t plus p minus 1. So 2 instances of degree reduction is needed. Now let us see how we can do the degree reduction with order of 1 cost, irrespective of which degree to which degree you go for, in the previous slide. This is going to work. So essentially, we take a bunch of sharings for which the degree has to be reduced. So we want to reduce from D1 to some D2, where D2 is smaller than D1. And we take a bunch of them, let's say t plus 1 of them, y, it will be clear in a while. So we take this t plus 1 bunch of sharings, and then we transform them through a RS style codes. So basically the sharings are linear, and we want to use a linear code, which is like RS code. So these are transformed to n number of sharings through this RS code. Okay? And this is going to take only local computation. Sharings are linear, and the transformation is also linear, so it takes just linear, it just takes local computation to derive all these sharings, n of them, and then the ith one is reconstructed just to the ith party. Okay? And then the ith party will reshare the same thing with the reduced degree, the degree that you want now, D2. But we can have the same problem, right? Some of these parties could be bad and they may not reshare the same values that it had reconstructed. But that's fine. That's why we had used this RS style coding, because over there after the resharing has been done, we can actually apply RS error correction on the resultant sharings, and we can get back the original ones. We can error correct, and that's again is going to be a local computation. You don't need any communication over there. Okay, so this is the technique that we use for order of 1 constant overhead degree reduction. And I guess that's all I have today. Thank you.
More questions for Arpita?
I know that all of it was information-theoretic. If I gave one-way functions, do you know roughly how the landscape will change?
So actually, we thought we had the lower bounds for the statistical case in the presence of one-way functions. Actually, we tried to model that with anything that is in the symmetric, mini crypt. So we wanted to model that as a random oracle and tried to see if we can derive the lower bounds. We thought we had, but actually it had some problem and we couldn't fix it, so we don't know. Yeah, earlier impression was that the lower bounds will hold good even in the presence of a random oracle.
Going back to the lower bounds for the circuit size, could it be that kind of like the right answer is in terms of the input, because you like this holds for these specific circuits for the circuit sizes, then you're in the input size?
Yeah, it could be. Yeah. So I guess the general question is very difficult, like for any given circuit. Yeah, that could be a difficult. Yeah, man.
Just the same point. I think that this lower bounds talks about the number of parties and not about the size of the circuit, and it's a bit misleading to present it this way, because we don't know whether in any of these settings, we don't know whether communication should scale with the size of the circuit.
Yeah, that's true. That's a bigger question that is still.
Yeah, but you know, when you present it like this, it seems like you said that this is settled. This is not settled. This is completely open, right?
Settled for the cases at least. Yeah, we
When
have
the
looked at
circuit
it.
is synthesized to be linear in the number of parties. So you talk about the number of parties. That's a fair question and it's meaningful, but it's not the question that you have.
Answered, yeah.
So we have for constant number of parties, we have counter examples that
Exactly.
Yes.
that it can be smaller than the representation size.
So it's not even that we don't know the answer, we know that the answer is false in some sense.
Other questions? If not, let's thank Arpita again.